Hi, my name is Loris Crow. I work at the Z Software Foundation. And of course, I've been working on a language server, naturally, but it's an HTML language server. So a language server for HTML. Now you might be puzzled by this choice, because of course, there should be a bajillion of language servers for HTML out there, right? You would think so, but let's see what happens using Visual Studio Code, like out of the box. So I turned my span into a spoon, and the thing doesn't complain. Which is, when I saw this, like, it was surprising, because if you think about it, like, okay, there are HTML linters, and there's also editors that are like dedicated to web development that will give you diagnostics, like they will show an error when you do this kind of stuff. Alex Petrov showed me that WebStorm does it, but at the same time, I'm using the most, like probably the world's most popular editor to edit the world's most popular file format, whether we like it or not, and still this is the experience. Let me show you instead what you get from my language server. So, thank you. So you get, I'm trying to close a spoon tag that was element that was never opened, so it complains, and it also says that now span is missing a closing tag. Keep in mind, I'm using another editor, but I'm not writing an editor. I'm writing a language server. So like this experience can also be had with Visual Studio Code. I'm just using a different editor so I don't have to fiddle during my presentation. But it doesn't end here. There is something more that my LSP does. So let me show you this other example. So here I have one span that I want to keep snugly fit to my to its content. That's fine. But let's imagine that this second line wants to have more space. So I put a space in there, and I have auto format on save enabled. So look what happens. So auto format on save, by adding some space at the beginning between the opening tag and the content, I'm requesting vertical alignment basically to my auto formatter. And this works also for example, here the text as well. Okay, last feature, and this one is heavily inspired, i.e. stolen from the Zig auto formatter. Sometimes you add attributes to your elements. Maybe you have a very long style attribute. I'm not going to ask you to raise your hands, but we all done it, even though we shouldn't. And at some point, you want to do vertical alignment of the attributes, right? So in my LSP, the point is that you negotiate with the LSP, you communicate with it by editing your code. And so here, if you add a space between the last attribute and the closing diamond bracket, look what happens on save. You get vertical alignment. And obviously, you can also go back. I'm going to remove the space now, save, and it goes back. OK, so I guess, what is my point here? I guess my point is that there's still a lot of missing pieces in all the things that still we even do today. Like everything, many of the things that we take for granted, man, they're not in good shape. Like there's a lot more that we could do. You just need to take a moment to think about it. And I also think that you do need a systems programming perspective to it. So that's basically kind of my point. Like learn systems programming and join the quote unquote revolution. I do think that there's like a bit of a renaissance in terms of systems programming. Also, maybe if you want to learn systems programming, you should consider learning Zig. Maybe you don't need to learn a system programming language to write an LSP. Maybe you can use something else. But I hope Andrew convinced you that you should not write an LSP in Python. To conclude, if you do end up learning Zig, or you think the world could use a better HTML LSP, which is the one that I'm writing, so you want to support my work, consider donating to the Z Software Foundation. Thank you.
Hello, everybody. I hope you're all enjoying the conference so far. This is a really unique and very incredible conference. So I'm really excited to give this talk today, especially to this room, where there's just so much distributed systems talent. Thank you to Natalie and Tiger Beetle for setting up this lightning session. The talk I'm going to be giving is on this concept of zero downtime, and we'll talk about what that means to us at Loophole in a bit. But for most of the folks in this room, especially all you database people, it's kind of like the holy grail of your infrastructure, right? And in a lot of cases, it's straight up impossible, or at least quite difficult to achieve. But we're going to do our best to achieve it today in our own special loophole way. And so I should explain who I am first. My name is Shiv. I'm the founder of a startup called Loophole Labs. That's my Twitter, my GitHub, my LinkedIn. If you're following along with what we're doing, those are the ones for the company, of course. So what is zero downtime? Or what does it mean to us at Loophole? Or maybe in the context of this talk. It means, can we take any stateful application, right? So think Redis, Postgres, running on a virtual machine or a Kubernetes cluster somewhere, and migrate it between nodes, right? So without interrupting it. And so the app has to stay alive the whole time. One moment your app is running on node A, and the next is on node B. You're not shutting down and restarting it. It's the same instance. It just magically moves and keeps chugging along. And in fact, the application itself shouldn't be able to tell that it's moved. And clients shouldn't be able to tell that it's moved. It's like a stateful migration, right? And then if we're speaking of your various clients, and we want to have some fun, can we keep the network alive while we do the migration, even if we're going between cloud providers? And then, if that's not enough, can we do it anywhere? So can we go between, regions? Can we go between cloud providers? Or if we're going to go all the way, can we go between continents, like one side of the United States to the other side of the United States? So that's what we mean by zero downtime at Loophole. It's what we mean by the holy grail of infrastructure. It's a very lofty goal. And we're saying, can I take any application from anywhere to anywhere? And we're not setting ourselves a lot of restrictions. Can it be done to this very impossible extent? And so the short answer is it can in a couple different ways, but we'll talk about a really good one today because I don't have a lot of time. And at this point, I usually explain a little bit of background, all the technical challenges, but with this audience, you guys can already see the various problems that are popping up. So I'm going to skip that and instead say, I'm going to do a demo, so just believe me for a second, okay? And I don't have a lot of time to explain this, so if you actually want to learn about how what I'm about to show you works, just come find me. I'm here until Sunday, and I'm happy to explain it. Most of it's going to be open source, and some of it's already open source. Okay, so I'm going to move Redis from one side of the United States to the other side of the United States while connected to it on an existing TCP connection from my laptop. And so we put together this really simple application. All it does is plot the latency for set or get operations when you're connected to a Redis instance. It does not handle reconnects. It's vanilla protocol. We haven't modified the server. We haven't modified the client. We just took a Docker container. In fact, we took the Valkey Docker container. Okay, so to do the demo, I think best way is for me to do that. Okay, good. And what I should do here, if you guys can see, great. I'm going to quickly start Redis. We just put together a simple API here, so maybe if I zoom in. Good, you can see that I am starting it in Miami. Okay, so we got a bare metal box in Miami, and I'm going to start a Redis VM. Takes a second, should be running. Then I have my Valkey instance, or my latency instance loaded up. It's got the URL already ready to go. I'm going to click OK. And so every 50 milliseconds, we're going to do a set operation. We're going to plot it. Okay, so you can see the latency is, God, what is it? 80-ish milliseconds. Makes sense. We're in Miami. Okay, we're going to take this instance and we are going to send it to Atlanta. I'm going to go back here. I'm going to press paste. And with that, the migration's on its way. So you can see, no downtime. All this latency we're seeing is very much the internet. Like, we're not touching the network traffic right now. So any spikes or anything you see, there's a very specific shape that you see when the migration happens. So we're still going. Let's see. Should take just under 30 seconds. There we go. Okay. So specific shape. What's the specific shape? It's the latency got better. Why? Why did the latency get better on this existing TCP connection? It is because we moved it closer to us. Okay, so we are able to reorganize the network traffic in real time, as well as moving the data, as well as moving the compute and all that. And a lot of this is open source. So I can do this again. How much time do I have? 30 seconds. All right. In fact, I'm not going to do it again. I'll show you guys the other ones. We can move it all the way to New York. But if there's any questions, I guess I'll take them now.
Everyone, I'm MA. I work on denormalized, and yeah, I don't have slides. Halfway through, I realized this talk should really be a tweet, so I'm just going to read off of my notes here. Yeah, speaking of tweets, there's I think it's a VC Twitter hot take, that everyone agrees with, I think, is that the history of software has been like the cycles of bundling and unbundling, and it has been very evident, especially in the world of databases. The MapReduce paper came out about 20 years ago, and along with giving us the term big data, it also gave us, things like Hadoop and various things in its ecosystem named after toys owned by Doug Cutting's children. So, and that was followed by a bunch of MPP databases named after wildlife in the African savannah. And then came Spark, which back then I was working, at an ad tech exchange, and, Spark was like an instant, life improvement for me, because it gave us like a nice functional data flow API in memory compute, and for the first time in this world, an actual shell that you could look against. But then, since then, we haven't really seen much in the space, right? And since 20 years, the world has come a long way. Since jerry-rigged Pentium 3s in a Mountain View basement by Jeff Dean was like the state of the art, but we have kind of stopped there. Except recently, there's been a lot more work here. And DuckDB, which I think isn't news to anyone in this room, but bears reiteration, is a C++-based OLAP query engine designed to run well on a single node. They have extremely optimized disk I/O and also memory layout that allows it to use modern computer architectures and the caches on them. And it performs really well. Actually, I think MotherDucks, they had a recent blog out about how they claim to have improved 25x over the last 3 years, and they can do data sets 10x the size that they originally intended to. Again, that's their marketing material, so I don't know, even if you do it by half, it's still good. And yeah, when you look at the TIPC-H benchmarks, it actually outshines Spark and Snowflakes of the world for workloads up to 1 terabyte, and yesterday someone mentioned the paper scalability, but at what cost, and this actually is a real life example of, a single threaded implementation outcompeting, yes, you could argue that it is highly parallel to that single node, but again, it's a real life example of this, right? So for many standard workloads, especially the ones against data lakes on object stores, there's no point paying BigQuery or Databricks for compute that you absolutely don't need to chart dashboards that some executive demanded but will never actually see. In fact, I think the DuckDB's marketing slogan should be "Save the environment, run fewer JVMs." So now to the world of streaming. It's a world that I particularly care about. And that's what me and my co-founder, Matt, who I cannot scan in this room, oh, well, he's back there, have been working on, right? So given that about 1 terabyte workloads work really well on a single node, it's a little insane to me that the state of the art in stream processing is running a Flink cluster just to grok at even Kafka topics with few tens of thousands of events per second. And yeah, and I actually worked at a popular ride-sharing company. So did my co-founder, but competing ones. And even there, our workloads rarely hit more than a couple of 100,000 events per second, and this world still requires you to run a distributed cluster, and that is actually what makes stream processing really hard, because your data is moving effectively in time and space, and you have to make sense about it. So yeah, so we're working on bringing the DuckDB experience to this particular world. Over the last couple of months, we have worked alongside Data Fusion. Arrow Data Fusion is a Rust-based query engine, and Arrow is an in-memory format, memory layout format that is designed for optimized SIMD compute. We are currently upstreaming a lot of this work into Data Fusion as a part of Data Fusion streaming, and we're benchmarking it, so I don't have any interesting demos to share. But yeah, we see really good speed ups on a lot of traditional stateful Flink processing workloads without the travails of distributed snapshotting. Because if you ever find yourself implementing an algorithm, there's just a few people in this room who I would trust to implement it correctly. I'm not one of them. So yeah, so you can so our argument is you can absolutely do this without using distributed systems for most workloads. Yeah, and the talk is sometimes, emphasis on sometimes, because it would be an anti-talk at this conference. But yeah, thank you.
All right, so I'm not really a distributed systems person, but I am a systems person. So this is going to try to be a fun talk. Let's get started. My name is Nathan Bourgeois. my Discord handle is there, and there's my GitHub. I work as reverse engineering and cybersecurity at Cedar Creek Software. Some of the stuff I've done is wrote a PSP toolchain using Zig, and I'm working on a project called Crosscraft. Crosscraft is a Minecraft implementation of Minecraft Classic and Survival Test, and we hope to do more to come. It's massively multiplayer, or multi-platform, so you can use it on Mac, Linux, Windows, and even consoles like the PlayStation Portable, the Vita, the 3DS. The client's written in C++, and the server is written in Zig, and the client is being rewritten in Zig. Cool. So, background, what is a voxel? A voxel essentially is the concept of a 3D pixel with a fixed dimensions. It has integral position, and typically you use a Cartesian coordinate space to determine where they are. A good example of a voxel game might be this game that nobody's ever heard of called Minecraft. And this is my peak 2014 wallpaper. So procedural generation is the way that most of these voxel games are being generated. So how do we actually make a 3D world? You have several choices about the dimensionality. It could be limited or infinite. If it's limited, it's usually a fixed size, and that's trivially computable and storable. However, the more interesting problem domain is in infinite worlds, which are hard. They have unlimited size, with an asterisk, and you have a lot of issues with storing that amount of data. So some of the properties that we use to generate procedural terrain are that they're idempotent. So if you give a particular world generator the same seed, you expect to get the same world back. It's multi-scalar, so you can change what resolution at which you are generating at. So the typical resolution is called a chunk, and that can be any number of X, Y, Z coordinate voxel dimensions. It's perfectly parallelizable because you can do everything in parallel. It's the same algorithm, and it's based on some simple noise algorithms, usually Perlin noise, simplex noise, or more advanced fractal Brownian motion. You generally have a combination of multiple maps. There's a biome map, which is usually a cellular noise or some other type of discrete noise, which influences the noise profile of the height map. The height map is a 2D map of altitudes, so that's how tall the world is. And there's also the concept of a density map, which is where solid and empty spaces are. And you can think of this as for generating things like caves, but you could also use it for oceans, lakes, and other purposes like that. So the data problem. If you want to store all blocks in a Minecraft world, which is 16 bits per block and 8 bits lighting, you would need 965 petabytes. Do any of you have that in your computer? So we get into the problem with saves and state, and it took me this long to get to the problem. So some of the Minecraft techniques that are interesting is the alpha level format essentially is just each and every individual chunk is just compressed and stored right there. The next step up that they decided to make was in the regions format, which was a 32 by 32-bit area of chunks, and they compress each chunk individually. In the Anvil format, they do actually start to make some optimizations. So if a chunk is empty, they're not going to store it. So this is like an air block that's just in the middle of like the sky. You don't need to store it. There's optimizations that were changed for compression and some of the world data changes. However, Anvil is pretty insufficient. It scales with explored world space, so you end up still getting the problem of the more you play the game, the larger your save becomes, and your save becomes like multiple gigabytes very quickly. Even with Anvil and the optimal compression, the estimated Minecraft storage space is about 100 petabytes. Storage of biome data is also insufficient for the mitigation of world generation changes. Just because a biome has changed or is the same doesn't mean that the actual noise profile of the biome hasn't changed. So what can we do to solve this? And this is really the heart of the talk, where we're trying to put all the pieces together, and this is a better save. So generation is idempotent. So realistically, we don't even need to store any of the data of the chunks that do not change, because we can just use the noise generation algorithm to get back the same result. The second thing we can do is differential chunks. We only need to really store what the player does to change from each block from the base value. So we can just store that delta instead. Another way to fix this is keeping old generators, which will mean that we can keep compatibility with old generations, meaning we don't have to store everything, and we can remove excess data like lighting, biomes, height maps, and everything else that can be recalculated. So if you're writing a procedurally generated game, solve problems and don't follow others blindly. Thanks.
We've
we've heard a lot about this already, and we've heard a lot about how hard it is, and I'm hopefully going to be able to convince you that it's actually not that hard to at least get started. So the reason why we're doing this is because we built this wide columnar database called FrostDB. Not going to be talking about this today. And really the reason is we don't want to become one of those Jepsen reports once at some point in the future. And so we pretty quickly, reached for deterministic simulation testing. And we had this preconceived idea as well that we needed to make sure that our entire code base, that we think about this before we even start writing our database, that we need to design everything, that we need to pick the right language. And we had actually already written our database in Go, right? So when we started to think about this more seriously, we were like, oh my God, no, we need to now rewrite absolutely everything we've done because Go is terrible for deterministic simulation testing. At least we thought so. So at first we were just like, okay, even if we don't get 100% there, how can we get 80% there? So the very first thing that you need to do, and this is actually more general, whenever you want to do this type of thing, you want to write a test that basically just performs a random set of things against your system. And this is even the case for things like antithesis or all the other simulators that have been created. And then the other thing that is actually really important is that you actually make your system deterministic. And Go actually makes a bunch of things intentionally non-deterministic. So that's Go routine scheduling, the switch case statements, map iterations. Go works really hard that you don't have only a single operating system thread. You want to be able to speed up time or slow down time, and ultimately you want to be able to simulate random failures. And I just want to walk you through kind of what this looks like for us. And there's a bunch of simplifications, but in essence, this is what it really looks like. So we have a bunch of probabilities of commands that we can run against our system, and then we just do 1,000 of those operations against our database, and they all have different probabilities of how likely it is that we will be running those next. And that kind of roughly corresponds to what we think the real world usage of our system looks like. And again, Go intentionally has a bunch of things that are non-deterministic. However, we realized that the Go runtime has actually done a really great job at centralizing all of those non-deterministic things, because the Go runtime basically, at initialization of the runtime, once seeds these random things, which it then uses to make the map iterations random, and all these other things that are intentionally non-deterministic. So we just maintain a fork of the Go runtime, and we have also proposed this change to the Go runtime, where we can basically just, outside of the runtime, generate a random seed and then eject it during testing. Then again, there's this really wonderful thing where you think you can control how many operating system threads Go runs on, and it's absolutely a lie. Yeah, you should check out this thread. But basically, the way that we solve this is by compiling our test suite to WASI, where we can actually then force it at execution onto a single operating system thread. And then we got lucky that the Go runtime has actually solved time for us. This is one of the hardest things to actually solve when you want to, speed up time. And the Go runtime actually created this because they have this Go playground where you can go online and just kind of execute random code. And they want to make that kind of reliable so that you can do a time.sleep of 10 years, and it will actually, execute. But what they do is they basically don't actually wait. They immediately fast forward until the point where all Go routines end up in a deadlock and only then continue. And so we basically just make use of this. And then the very last thing is Go has this thing called cooperative preemption, where basically at any point in time, your Go routine can stop executing. And we just, again, got super lucky. This just doesn't exist on the WASI target. So that's how we do that. And then ultimately, now we control the WASM runtime, which we then use to inject random failures at, because we control the entire syscall interface, where we can now not just deterministically plan all the things that we're going to do against our system, but also deterministically plan all the failures that we're going to be injecting. And we found a bunch of crashes, a bunch of duplicate writes, a bunch of data loss things that never actually reached production because of this. And this is how we're this is how we're increasing confidence one simulation at a time. Thank you.
Hi, I'm Galen. This is my Twitter handle, if you want to follow me. I'm going to be talking about turning development environments inside out. I spent the last 4 years of my life working on tools to make development and testing environments as close to production as possible. Like, why do you want to do that? The idea is the closer your dev or test environment is to prod, and the earlier you get access to it in your dev cycle, the more likely you are to catch bugs faster, especially those bugs that like only appear in prod. So our first approach to this, let's imagine this is kind of what your prod environment looks like as a holistic application. Our first approach to this, it's what a lot of people do, try to like wrap a container around the environment, extending the idea of what Docker did for one process, but to the entire environment. And if you do that, theoretically, you can run it on all of your developer machines, or maybe in remote sandboxes. Either way, it's the same principle. You have a similar developer experience you would get with Docker Compose or with Helm charts on Tilt. You're running a production-like thing on your laptops. A lot of modern infrastructure as code approaches follow this approach, and the idea there is let's use the same environment definition in dev as you use in prod. There are some issues with this. What are the things that you can put in the container? Well, the services you host yourself. What can't you put in there? You can't put your prod data in there. You can't put any managed services in there, like good luck putting Stripe on your laptop. And you can't put traffic in there either. So the problem is that's a big surface area of bugs that will hit you like once you go to prod. So we took a new approach. We turned that whole thing inside out. And our new approach is instead of putting production, in quotes, it's not really production, into your dev and test workflows, we're going to put your dev and test workflows into production. Those quotes are intentional. It's into production. I know it sounds crazy, but hear me out. We'll see what it looks like. So this is not a live demo. I took pictures so it wouldn't break. This is this is the UX of like a voting app, classic Azure voting app demo. The infrastructure in Kubernetes here looks like this. Traffic comes in through the front end in this gateway. You have a service that processes votes, and then it stores it in Redis as a data store. This is what production looks like. If you're going to use this new approach, we call it Cardinal. You can run this command, Cardinal create devflow voting app. We call it a devflow for a good reason. You'll see why in a second. Once you run this, what happens is your dev version, which here is represented by V2, gets deployed alongside your prod version. You can manage traffic splits via routing policies. And then for any stateful services, for example, Redis, you're going to have a little sidecar on top of it that is going to manage write isolation or complete isolation if you want to. And then what you have is isolation that's defined by traffic routing policies and these data source specific sidecars rather than by duplicating everything in every environment that you have. This is the new approach we have, and you can imagine a lot of people doing this, and your cluster is going to look pretty wild. You're going to have a lot of people deploying dev versions everywhere, but the advantage here is you get much closer to production with good isolation guarantees still, and also you can do everything in one environment without needing to manage 20, 50, 100 different environments, depending on what kind of tests and what kind of scale of sandboxes you're doing. So advantages to this, you can catch bugs that only appear in prod faster, especially if you don't have like a serious compliance requirement where you can never touch prod. You can stop maintaining multiple environments. You can do it all in one. And it's also a lighter weight dev workflow. You're only deploying your service, not a bunch of other ones. You get to reuse everyone else's deployed services. Disadvantages, it's a very unproven isolation technique. You're isolating by routing and database sidecars rather than by whole environments. And also, our sidecars would need to support your stateful services. So depending on how many different stateful services you use, there's a wide area of support. And other disadvantage, it doesn't really exist yet. It's a POC, just a demo. So if it's interesting to you, joined the beta and star repo. We opened the repo like yesterday, so it's got 9 stars. So you can help us out there. That's the repo. And the biggest thing we need right now is feedback. And if it's a compelling thing, join our early community, and we'll get the right stateful support for your services as fast as possible. That's it.
Hey everyone, I'm Raghav from Figma, and I'm going to be talking about small stuffed maps. This presentation is in light mode, so some of you may not be used to that. Please adjust accordingly. So what am I talking about here? Let's talk about a Figma file and how it's represented in 1 minute, if I can. So a Figma file here on the left, let's say we have a frame, which is that rectangle, triangle, and an ellipse. We have a server that also has the same copy of that file, and it's stored in memory as just a list of those nodes. So a frame, a triangle, and an ellipse. And because it's all stored in memory, we end up giving Jeff Bezos a lot of money because storing things in memory is expensive. But we do have to store it in memory because if you've used Figma, it's a low latency communication scheme, and we want to keep things in memory so we don't have to do an S3 write or a DP write for every one of these changes. Let's talk about one of these objects in particular. Let's just take the frame we were looking at the previous slide. It's a bag of properties. We have a type, frame, color, white. It's not quite like that, though. It's really, the type is a pointer into a byte slice that tells us it's a frame, and the color is a pointer into the same byte slice that tells us it's white. Okay, but it's not actually like that. It's actually, instead of type and color, we just have some indexes, similar to protobuf, where every field has an ID. We use a similar format. And so we have 0 that maps to frame, and 1 that maps to white. And then our sort of code generation layer knows what these numbers and field mappings are, and so we can give you ergonomic APIs. So why is this last bit important? When we measured where our memory usage was the most, we saw that this bottom layer of the stack, which really is just a map of a U16 to a pointer, that's where most of the memory was going, which is kind of surprising because this is all just metadata. It's not actually even data. It's just telling us where to go to get the actual data. And if you look at this map, it's a small map because the U16 here is actually just a field number that a user has to go and type into a schema. So one of them could be a type, could be a color, could be a shape, but it's a small map. There's going to be a limited number of fields. I think we have like 200 today. And so you can see that it's not going to become very large. And again, remember, our goal is to make this cheap. OK, so let's just define a benchmark. Let's say we have 10,000 nodes in this Figma file, and each of these nodes is a map that we were talking about in the last slide. And in this small map, let's say we have 50 fields. Let's try a couple of obvious maps that we all would use and what we were using earlier in our deserialization library. Let's start off with a hash map. We have benchmarks on the nanoseconds per insert, nanoseconds per fetch, and the memory use in megabytes. Just one thing to note is we don't care too much about the insert and fetch times for our particular use case as long as they don't regress too badly. So we want to keep an eye on them, but we're mainly trying to optimize memory use here. And a B-tree map just does better than the hash map when we see it. Let's try and define the simplest sort of structure that's the most memory efficient that we can think of. So if we have a map and we just store everything in a flat list, that's pretty memory efficient, right? We're not like doing anything complicated. It turns out that's pretty memory efficient, but it also does slow things down a decent amount. So if we just add one additional optimization on top of that, where we store a sorted list of keys and values and use binary search to insert into this map, and similarly binary search to find in this map, we get pretty good performance. One thing you may note is that the insert operation here could potentially be bad if you're inserting in the middle of this map, because you have to now shift all the elements. But in practice, again, it's a small map, so a lot of these things don't matter as much for our particular workload. So when we actually look at how well this performs, we see that we actually get a speed up in our insertion times. I think this is an artifact of the benchmark. We also have quicker fetches, which may actually be true because, again, maybe just loading the entire vector into memory, and that's really quick for a CPU for these small maps. And our memory use is much lower, as we expected. Yay. But can we do better? Yeah. Yeah? So I know we said we did the best when we stacked everything into a vector, but if we look really, really closely at this, we're storing a U16 and a pointer. But what is a pointer? Data. Pointer is data. A pointer is 64 bits of data, which maps to 18 exabytes of addressable memory. We're not paying Jeff Bezos that much money. What a pointer really is on most x86 systems it looks like this. There's 48 bits of addressable memory, and the top 16 bits are kind of not used today. Caveats I'll get into later. And if you squint really closely, the 16 bits just coincidentally happens to be the 16 bits we need to store the field ID. Great. So now we have a pointer that we can use bit masking to store the top 16 bits as our field ID, and the bottom 16 bits as our pointer. Let's do this. Even better insertion times, the same fetch times, and even lower memory use. I would expect the memory use to be a lot lower. I'm not sure why it isn't, but there could be a bunch of reasons. We're measuring RSS here.
Ding, ding, ding.
So it could be an artifact of malloc and things like that. All right, I'm just gonna quickly go. Cool.
Okay, so who has used React.js? Probably in anger for this audience. Okay. What Electric Clojure is an experimental programming language approach to user interfaces. We try to solve the front and back end connection, the network connection with the compiler. So as an example app, this is a full stack web app. There is a clock on the client, a clock on the server, and we're subtracting them, okay? And here is the source code for that application. It's 12 lines. We have a function, and what we do is we mark the client and the server regions. So here on the client, we have the system time MS, that's a clock, and we also have a clock on the server bound to the C and S variables, and then we just subtract them here with the normal subtraction operator. And so what happens is this macro compiles this code down, it analyzes the Clojure syntax and compiles it to a DAG, and then does like a coloring to sort out the client and the server regions and compiles it to a backend program, which compiles down to the JVM, and a front-end program, which compiles down to the browser. And because they know each other's source codes, these programs are able to coordinate. Therefore, when the server clock ticks, the S, it sends us a message over WebSocket to the client, which receives it, and then knows to update the subtract function, and then it propagates to the DAG, just like any other reactivity framework. So the goal of this paradigm is to give you abstraction. The essence of systems is having solid, robust abstractions. Abstraction to us in programming languages is Lambda. With Lambda, you can build anything. You can build an operating system. You can build Emacs. So what we promise is that we preserve function composition rules. This is a real function, but yet it has front-end and back-end parts. And the reason this works is because it's already an asynchronous program. The reactive paradigm is asynchronous. So adding like a 10 millisecond WebSocket hop is fine. There is not an impedance mismatch with that. Okay? So now I'm going to show you a stress test. So what does it mean to have Lambda? Well, for example, if you studied Lambda calculus in programming languages, you can have the Y Combinator. So the Y Combinator is a way to implement recursion itself with nothing but Lambda. So if you have a programming language that doesn't have recursion, you can use the Y Combinator to implement recursion. So this takes like 4 hours to look at and understand how the Y Combinator works. We don't have time for that. The point is, this is Y, okay? So given Y, you can inject recursion into a function. So here's your recursion that's been injected. So here is a Fibonacci function defined in Electric Clojure, okay? And it is just Clojure syntax here, and you recur and whatever. So there is no client-server regions here. This is just to help us understand what's happening. So we have recursive Fibonacci, actually factorial, I think that's a typo. And here's the result, okay? So the point is, Electric, it's truly Lambda, it works. Okay, so what do you get if you have Lambda? Here's a more complicated demo. We are going to use a Y Combinator to traverse the file system recursively on the server and recursively transfer it and render it to the DOM as you recursively traverse it, okay? So let's look at the source code for this. First, here it is, whatever. So we have a reactive front end with the DOM over the file system on the back end. Here's Y, and here's our recursive tree. And so, okay, we have an if statement in Clojure. We check if the file is a directory. Oh, we have to insert the file that we start with. So let's look at the entry point. Here, Clojure Java IO file for the source directory. And then we call our recursive function here with the file handle, which is like a Java reference on the back end. It doesn't serialize. So here's an if statement. If it's a directory, switch to the client. Start rendering to the DOM. What's the text here? Oh, better switch to the server. What's the file name of that handle? And remember, this is a Java reference. It doesn't serialize. It's on the server, okay? Go back to the client. Render it to the list, the UL and the DOM. Go back to the server for the children. You need a for loop. What is the list of files at that point? Okay, and that's in a for loop. So we're iterating in parallel reactively. And now recursion. Call the function again. Back to the top. Is it a directory? Render it to the LI, etc. So the point is this works. The compiler will just zip through this, and it's actually efficient. Like the core insight here is that if you like draw this as a flowchart and you paint like blue the server parts and pink the client parts, there's actually no spurious request waterfalls. It like lifts apart perfectly, and you get a laminar. Am I done? You get a laminar smooth data flow loop, and it's super fast. So this is electric Clojure. You should Google electric Clojure. Check it out.
Hi, I'm Andre, this is Andrew. So we're going to talk about the project that we've been working on, Side-Eye. Side-Eye is a debugger for distributed systems. So to start off, how do we currently understand our production systems and our particularly complex systems, right? Well, we've read the blogs, we do the instrumentation thing, we instrument the code with logs, with metrics, with traces. And then we use monitoring tools to visualize them, right? And then what do we do when these don't answer the question that we have? What happens when we have a question that was not anticipated by this instrumentation that we programmed into our system? Well, we're back to printf debugging, right? But for printf, you know, for adding any more instrumentation, you need to change your software, you need to recompile it, change the source code, right? And that's not something that's tractable to do for production environments. But there used to be a better way, right? There used to be a tool that allowed you to interact with your software in a more arbitrary way, right? We used to have this thing called a debugger. And the debugger was a very interesting observability tool because it let you ask anything out of your program, right? You could ask questions that were not anticipated when the source code was written. You would form the questions by poking into the memory of the processes that you're inspecting, right? And the other amazing thing about the debugger was that it was interactive. You'd ask a question, you'd quickly get an answer, quickly ask another question to validate your hypothesis. And that all sounds great, but debuggers don't quite apply to current systems, right? What's the last time that you attached a GDB to your production environment, right? You cannot do it. It's too dangerous, it's too slow, it just doesn't apply, right? And even if you could attach GDB to your processes, you could do it to one process at a time because that's how GDB works, right? So that doesn't map to our distributed systems, right? And even if it did apply, it'd still not be quite the tool you want, right? Because you do not want your debugging sessions to start from a blinking cursor, right? You want to build on the work that other members of the team or you have done over time, right? Okay, so if GDB doesn't work, we've been working on a product or a debugger that does work, right? And so how is it different? Well, at the low level technology is very different, right? We extract data from running processes in a much safer and much quicker way than the kind of technology that traditional debuggers use, right? We compile probes based on the debug information, and we use dynamic instrumentation to inject these probes into your running processes, right? And that's at the low level, but at the high level, Side-Eye looks very different from something like GDB, right? It doesn't give you a blinking prompt. It's a product that scales with a team and that a group of people can collaborate on a debugging session over time. Right? And maybe I'll let Andrew give a little demo. Yeah?
All right, so this will be somewhat live. So here you can look at kind of past snapshots of point in time. This is pointed at a real live production cockroach cluster, cockroach DB. There's 3 nodes. We can get the node IDs, which we'll read out of memory. And you can get kind of an overview of the Go routines as a flame graph, but you can also look at the data in kind of a tabular format that's derived from the functions that we're tracing, and we can look at things like the running SQL statements, and we can look at all the statements that were running at a given point in time when this was taken. And then we can go look at this Go routine that's been running for the longest amount of time, and this we can get its stack trace. And we can actually see data from the functions of this executing statement. We can see placeholders into the SQL statement, and we can scroll down this stack trace and observe that actually it is in the key value store, sending a key value store request, which we can look at the like body of the actual GET request and things like the key. And then you can get to, oh, it's in gRPC, and here's the network address and the stream ID, and maybe it'd be cool to see the server side of that. So we can jump across and see, okay, now we're on another machine. And here's the server side processing of this key value request. And oh, we're blocked on like a lock somewhere. And we can see, okay, who's the transaction that's holding that lock? And we can go and look at that transaction and see, you know, the placeholders of its statements and which accounts it's locked on. So we're running out of time, but this allows you to kind of capture new data in real time. And this is kind of point in time, but you can also, we're working on features to inject log lines and add dynamic instrumentation to your real production systems with very low overhead.
Hello. I'm Mukaram, but that doesn't really matter. I'm going to be talking about, I just want to introduce the concept of a multi-kernel, because I think a lot of people don't know about it, and I think it's really cool. So let's get started. So this is sort of a comparison diagram between like common kernel designs. So on the left, we have like what looks like what you're probably used to, a monolithic kernel. So you can see like if you have a single CPU, that's the thing on the bottom. It has 2 cores. There's a single kernel that runs on the whole CPU. And you know, all the drivers and everything sort of lives in the same space. And then you have processors on top that you know, are virtualized by the kernel. You've probably heard of microkernels, which is basically saying, you know, the monolithic kernel, it has maybe a bit too much stuff in it. So let's split out some of the things. So you know, we have like maybe move the drivers and maybe parts of the scheduler and these things into separate processes. But you can go even further and say, well, actually, we have multiple cores. And cores are kind of like separate processors. And you know, it's kind of like separate computers. What if we just ran a completely different kernel on every core? And that's basically what a multi-kernel is. So why is this useful? There's a lot of reasons. So one is it gets you a lot of extra capabilities. For instance, now you can apply a lot of distributed systems algorithms. If you want to have 0 downtime kernel upgrades, you can do that. If you want to do, if you want to like add and remove processors, again with 0 downtime, you can do that. You know, if you want to have a computer that has a CPU where multiple cores are, or you know, you might have multiple CPUs on the same motherboard, and you want to say like, oh, these are actually different architectures, and then when I context switch, or I move a process from one core to another, it automatically jumps into a hypervisor. You can do that. You want to, and honestly, the biggest thing for me is basically like performance and just like better code quality. So performance is because on modern machines, we keep adding more cores, like line goes up, right? But performance doesn't really go up because you tend to hit scalability bottlenecks because you have contention in shared memory systems. So current kernels don't scale well to high core count machines. And as it turns out, when you start writing everything in terms of message passing and you have a separate kernel in every core, you can actually optimize this much better because you're expressing the problem much more naturally. The other thing is, since every kernel is running on a single core, you can say, well, we have a shared nothing architecture, and it's all straight line, single threaded. Actually, you can just abolish the concept of threads. And you know, it's pretty great. Like your code is simpler, you can more easily test it, and yeah, that's. I hope that was somewhat convincing. Well, and the power efficiency thing, you know, if you want to like shut down a core to save some energy, you can do that. So what's the deal? Why have you not heard of this? Here's like some anti-Unix propaganda. I was going to add the Unix Haters Handbook, but I forgot. But you should also read that. And if you want to read more about this, here's a reference. It's this paper from OSDI 14. And in particular, there's like a long-running research project, which is kind of over now, called Barrelfish, mostly based at the ETH in Zurich. Highly recommend checking it out. And with there, I'll end my talk.
Okay, so I'm just going to talk about making a terminal emulator really, really fast. For the past 2 years, I've been working on a terminator called Ghostty. There's a few dozen of you beta testers that are in the room. It is the world's fastest terminal emulator, but it's not public, so you could go ahead and not believe me for now, but I'm going to talk about how I made it really, really fast. What is fast? What am I measuring? So these are the 4 things I'm going to talk about. I actually skip input latency because I'm going to run out of time. Plain text I/O reading, escape sequence, processing, and then renderer speed, and then input latency. So I'll explain each one. So plain text I/O, let's start with English, because English and ASCII in particular is very, very common. So here's Ghostty reading a 5 megabyte file. Just cat, right? We're just testing throughput. I do it a few times. You get about 54 milliseconds on the cat. Here's iTerm doing it. 114 milliseconds, about double and some change. iTerm's pretty slow though, so here's Alacrity doing it. And pretty fast, pretty close to Ghostty, only a few milliseconds slower. English is pretty simple, so that's not that hard. And for people who say this doesn't matter, you know, how many of us have accidentally catted a very large file and we've been like, you know what, we're just going to force quit this because it's screwed. You don't have to with Ghostty, it'll just be done. Okay, let's do plain text I/O with Japanese. We're just randomly picking Japanese. It's a language I read and speak, but any international language would matter. This is more complicated because you're going to be doing font fallback probably, and the characters are bigger. They're not just 8-bit anymore. Okay, so let's see Ghostty read a 5 megabyte Japanese file. It's faster than plain ASCII. 50 milliseconds, okay? 50 milliseconds, iTerm 2 doing it. 475 milliseconds. You could actually see it scroll. Ghostty, you couldn't really see it scroll. You can if you want to be pedantic about it. Alacrity, okay, but slower. And now we're actually in the realm of almost 20% slower than Ghostty. Again, doesn't matter. When you cat a binary file, a lot of garbage starts coming out, and Ghosty's going to crush in that scenario. Okay, so escape sequences. Escape sequences are how you control terminals. They start with an escape. Here's the random, I generate random escape sequences, and here's the throughput you get. You get 98 megabytes per second on Ghostty, 2 on iTerm, 2 really just like completely in the garbage, and Alacrity is 62 megabytes per second. I have no way to visualize this, so you just got to trust me, or run it yourself if you're in the beta. And then the renderer. The renderer is how fast, when you get a change in the terminal, you could actually see the change, or if you send an input, such as like a mouse event, how quickly you could reflect it. Here's Ghostty. Scrolling through that Japanese file top to bottom, and you can see at the top right, we're maintaining about 175 frames per second on this, and it goes up to 400, 500 at some time. I'm not able to reproduce this exact HUD because Ghostty uses metal directly, and no other terminal emulator uses metal directly, and that's the only way to get that HUD. Alacrity goes through an OpenGL translation later and all sorts of stuff. But if you're in the beta and you do it, you could feel it. Okay, so how did we go so fast? Number 1, we do SIMD escape sequence detection. This is the naive way to find escape sequences. You go through the bytes, and if the byte has an escape, you do it. Here's the way Ghostty does it. You go through chunks of bytes, usually around 16 plus at a time. If the chunk contains an escape sequence, you do it, and that has the same cost, same latency, close to the same latency on the CPU. So more or less what you end up getting. Here's the cost of a mem copy. On top, we're doing literally nothing. The scalar approach is about 380 milliseconds, and the SIMD one is 52, so it's about, what is that, 7 and a little bit times faster. Believe it or not, almost no terminal emulators do that. SIMD Unicode decoding. So this just uses an off-the-shelf GitHub project called SIMD UTF. Here's the benchmarks, literally doing nothing, not doing the Unicode decode, 22 milliseconds. The scalar approach is 344. The SIMD approach is faster than doing nothing because we're doing more bytes at a time. So we could actually decode Unicode faster than copying the bytes. And that's why we do really well in that. Pre-computed code point width. So code point width, when you get a character, we have to know how wide it is because we have to know how many cells it takes up in the terminal. Letter A is 1, this Japanese character is 2, which actually is the Hashimoto. And then this emoji is 2. Some emoji are 1, and it's a disaster, and we're not going to talk about that, but that's a whole thing. And here's what I did. So you could actually, Unicode code points are 21 bits. You could create a multi-level lookup table in order to compress it all. And what I ended up doing was I went over the full 21-bit space and pre-computed the width of every single one. And it fits within the L1 cache. So here's what you get. Literally doing nothing, 100 milliseconds, using WC width, this is in glibc, 358 milliseconds, using my pre-computed table, 194 milliseconds. Really fast. Pre-computed graphing break. Graphing break is if you're given 2 code points, is the code point part of the previous one, or is it a separate character? And a grapheme is something you see visually. So some emoji, East Asian languages, things like that, they don't fit in 21 bits, so it's actually multiple bits. And the length of a grapheme is actually infinite. It can be infinite. So you can't say they're going to fit within 4 bytes or anything. So grapheme break, this is the function, code point 1, code point 2 state gives you a Boolean state. Same thing, I computed that for the full 21-bit times 21-bit times 1 bit, because the state is 0 or 1, state space, and I pre-computed the entire thing. It also, in a slightly compressed way, fits in the L1 cache with the other table. So same thing, no-op 50 milliseconds, Ziglyph, which is a Unicode library that does the same thing as a lot of other Unicode libraries, 500 milliseconds, Ghostty 65 milliseconds to look it up. And here's the speed for getting the Japanese Bible, we don't even care. So use less memory is the first one. Use less memory makes things faster because it makes things more cache friendly. A terminal has rows, columns, cell contents, and style. The naive way to do that is an array of cells where each cell is this, right? But there's a few insights. Terminal grids aren't that big. What's visible at any given moment is roughly 100 columns by 40 rows. It's not that big. There's not a lot of unique styles. A lot of styles on your terminal are shared, or there's only empirically, we ran a bunch of software. Even NeoVim with the most complicated theme had about 25 unique styles on a full 6K display. Mostly single code point graphemes, and scrolling is super important. Rows move a lot, but cells don't move a lot sideways. So the solution is we lay it out like this. We have an array of rows. The rows are pointers to an array of cells that are in a single row. Instead of storing pointers, we store offsets from a base address, so we're able to go from 64 bits to 32 bits. We're trying to get that to 16 bits. A row is just a 64-bit integer with a bunch of packed data in it. A cell is just a 64-bit integer, and we have a look-aside table for styles and graphemes, and we just maintain the index in order to write really quickly to that. And we use a little bit of SIMD to write as well here. And the result is you save a bunch of memory. This was like what we used to have a memory. 20 empty windows used to use 730 megabytes with a certain size. Now it's 146 and things get smaller. But the point is things also got faster. So ASCII reading went from 191 to 166. Unicode reading went really faster because our layout was much better for these scenarios. And that's it. So that's those. There's a lot more techniques, but these are some of the things that go into building a terminal emulator. If you join the Discord and ping me and you're here, I'll invite you to the beta and you get source access and you could look at all this stuff. So thank you.